Hi everyone, welcome to today's customer exclusive webinar on simulation basics in CORE. My name is Katie and I will be your host during today's webinar presented by Bethany Maddox and Sara Sumner. We're excited to help you maximize your experience with behavior modeling today so you can get the absolute best of your system engineering efforts. Bethany serves Vitek's customers primarily at the support desk as a customer care specialist. Between support cases, she manages the overall vision of customer care at Vitek, developing instructional screencasts on various core and Genesis topics and elements of software documentation. She has often served as host, writer, and technical manager of countless webinars throughout her tenure at Vitek. Sara works as an applications engineer for Vitek, using her 12 years of practical systems engineering experience to guide Vitek customers through the methodology and tool advantages available to them in core and Genesis. Sara has experience working with a variety of industries, including defense, energy, and aerospace. Before Bethany and Sara get started, I have just a few housekeeping items. We will be answering questions today at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on your webinar control panel, and I will get them over to our presenters. The webinar is being recorded today, so if you experience any connection problems during the live presentation, a recording will be available on the My Support area of the Vitek website within 1 to 2 business days. I will send out a link to that page. In addition, this webinar today is part 2 of a 2-part series, so if you missed part 1, you'll find that webinar recording in that same area on our My Support page. I'm now going to turn the presentation over to Bethany and Sara. Welcome and thank you for joining us.
Hey guys! So in our last webinar, we learned the basics of behavior modeling to include detailed information on all of the behavior modeling constructs. So today, we're going to discuss and demonstrate to you guys how you can use the CORE Discrete Event Simulator to simulate the behavior model in your CORE project. So our agenda for today, we're going to talk about what is COREsim. We're going to discuss how we should use COREsim and why we should use COREsim. We're going to orient ourselves with the simulator, and we're going to provide a demonstration of COREsim to you guys. Okay, so what is COREsim? COREsim is a discrete event simulator. It's going to provide to you the automatic verification of operational and functional behavior within your system. COREsim can be used to correct your logical behavior, verifying that the current design will execute logically and the activities will execute and occur in the sequence in which they are intended. This is important as your system design grows and therefore becomes more complex as you work through the design layers. When your system does grow more complex, it becomes much more difficult to validate the logical behavior without the use of a simulator that can traverse through the logical decomposition of your system. COREsim is also used to analyze your system performance. Resources, architecture, design selection, and functional allocation can constrain the overall system performance. When you capture these constraints in the CORE model, you can assess the aggregate effects of these constraints on the performance of your system by executing the behavior models in CORE. By performing the execution, you can look at the results and correct or optimize your architecture or system design. So why should we use COREsim? Well, first off, we can use COREsim for dynamic analysis. We can assess the dynamic consistency of the system behavior. Now keep in mind that you are simulating the behavior in your underlying data model. So as you make changes, you can immediately simulate the changed model to see how your changes can impact your logical behavior. We can use it for timeline analysis. This will allow us to establish and analyze our integrated behavior timelines, and then we can adjust as needed on the fly any changes that need to be made, and then simulate those changes. We could perform resource analysis. As we said earlier, resource analysis is important because the resources constrain your system design. So the COREsim allows you to monitor the amount of system resources and will show you any discrepancies within your model. And then finally, we can perform flow analysis. So you can simulate any type of process flow within your system. You could even analyze flow of the items being passed on the links between your components during the execution of the timeline behavior. So now that we've talked about why we're going to use COREsim, we're going to discuss and show you an orientation of the core simulator. So you should see now an EFFBD that I have open for my system context. So I've opened this so you know where we could begin our simulation. So if I click the simulation button here, the simulator is going to open. Now, one thing to note that only one window per element can be open at a time. Multiple simulator display windows can be opened as long as they are on different elements. Now you will notice that the simulator right now is blank. The middle of the window is blank because we haven't run the simulation yet. So before we run the simulation, we're going to hit the reset button. The reset button will allow us to essentially reset the simulator based on any changes we made to our underlying data model or to our model preferences since the last simulation. After we hit the reset button, we're going to hit run. Okay, it said that the simulation is completed. And now we're going to talk about a little bit about what this looks like here. Okay, so you will see that underneath here, we have our scale control, our time, and our result detail. Our scale control allows us to scale the timeline on our screen. So right now we have a scale control of normal, but if I change that to large, notice how it just expands on the screen to make it a little bit easier for us to view the scale of our timeline. The time section is going to indicate the duration of the execution of the simulation. So notice our simulation ran for 79.99 units. The result detail will give us specific information based on anything that I have selected in my timeline. So if I select the execution of C11, you will see the result detail populated in the far right corner. It tells us when it began, when it ended, how long the duration was, and what is the value of that item. In the left side of the pane here, what you're going to see is you're going to see a list of elements that are encountered during the simulation. These elements can include behavior being performed, the resources that are utilized, triggering items, and any links. You can control which element classes are shown here through your user preferences. Currently, we're just showing the functions that were executed during our simulation. So now we're going to break down our timeline window. On the right side, we see the timeline that's going to detail when each function was performed. For functions, this will show when each function was performed and how long it took for the execution of that function. However, if we were to include resources, items, and links, it would tell the number of each available. And Bethany will show you more of that in detail in a little bit later. When you're viewing the timeline, you'll notice the different colored bars for each item on the timeline. These bars give you an indication of essentially what occurred during the simulation. So you notice the diagonal lines on C.1. This means that this function is essentially decomposed down into other functions. So the execution of the decomposed functions is actually going to validate that this function is going to execute as planned. The teal represents that a function executed normally. The yellow indicates that a trigger was received, and the green indicates that execution went normally after we received the trigger. You will see other colors on the timeline as well as you play around with the simulator. You will see magenta and red that will essentially show us that we are lacking resources and we need to check our underlying data model to essentially make changes based on that discrepancy. And again, Bethany will go through that in a little bit. Okay? You can save a completed timeline as a graphical file outside of Core by going to File, Save Diagram As, and this will allow you to save it wherever you choose. So now let's talk about the pull-down menus a bit. If we go to the View pull-down menu, this is going to allow us to change the view of our timeline. The time scale increments allows us to change the timeline scale here. So right now we have it set to 100. If I change that to 200 and say OK, you'll notice that it expands out to 200. And if applicable, this would allow us to see more of our execution that has performed. If I go back to our view, the show frame on output will just show a frame whenever you decide to output the diagram. The show transcript enables the transcript that you see at the bottom of the window. The show the timeline elements, we'll discuss that a little bit further later. And you can refresh your window and then change the toolbars that you're being shown on the simulator. The control allows us to essentially just control the simulation. So you can run the simulation, you can step through the simulation, you can stop the simulation, reset it, and then open a specific element based on what is shown here in the simulation. Now the control, you will also see those in these icons here. The step control is interesting because if you refresh this and then click on step, it will allow you to step through the execution of your behavior, and you can see as each function is going to execute in the sequence in which it executes. Okay? On the left-hand side, you see the ability to edit the order. You will notice that our functions here are not ordered in the sequence in which they are going to execute. Right now they are ordered numerically. If you wanted to edit this order, you can click Edit Order, and then you could just change the order in which the functions are going to show up on the left-hand side. Okay? However, note that if you do change the order, this does not in any way impact how the simulation will occur. So it does not change the order in which the functions are being simulated or executed. It just changed the order in which they appear. If you want to set it back to default, you can click on Recompute Order, and it'll go back to the default settings. The transcript window at the bottom corner is going to provide you a log of events as they occurred with information about each event. This is going to provide a basis of understanding the detailed execution of the behavior model, and this can be used for troubleshooting any errors or discrepancies found during the simulation. The transcript can be saved as a CSV file by going to File, Save Transcript As, and then you can save that off onto your computer. The Timeline Elements window you will see here, if you click this button, it's going to open up and it's going to allow us to change essentially what is going to be shown within our elements. Right now we are just showing functions as we spoke of earlier, but I could change that to show items, resources being utilized, and the links being passed, or the links between the components that are performing the behavior. Now notice the difference between the database elements and the simulation model elements. The database elements display each element only once, as it should occur only once within the database. However, the simulation model elements will display an element once for each time it's encountered in a simulation, because sometimes you will have an element that is encountered in a simulation more than once. If you want to change any of your default settings for your simulator, you can go to Tools, User Preferences. You'll notice a COREsim option, and then you could change your simulator preferences here. And this will change it as default, so then every time that you run the simulator, it will use these options to run the simulator. So now that you have an orientation of the simulator, I'm going to give control to Bethany so she can provide to you a brief demonstration of COREsim.
Okay, so this is where I pick doing today is merging some information. In part one of our webinar series a few months ago, we taught you about the different constructs and what they do and when you might use them. Sara's given you a fantastic orientation to the simulator. Now we're going to apply those things with some examples, and we're going to be working here in Core. I'm going to go ahead. I have set up a sample model here that is admittedly rigged to make this webinar go well, so you'll see me taking some shortcuts and using elements and whatnot that we've already created. So I'm starting here with the EFFBD of my top level element, but I haven't put anything in it. So let's just start by putting on a function. So we'll just drop first function on here, open up the simulator, and let's see what that looks like. Really simple. Now take a look at the timeline. We did not set the duration to tell Core how long this function is supposed to take, yet you'll notice that some time is referenced here. When you don't set the duration, Core will use a normal distribution that's going to have a mean of 10 and a standard deviation of 1. Using defaults like this are great for use early in your model development. As your model matures, you're going to want to set these. So let me show you where you do that. You do it on the property sheet of the element. So I can just open up first function, and we see the duration field here. I can click the edit button, and we have some options to set that. You can set it to a constant, random, or utilize a script. Also take a look at the transcript down here. Sara also gave you an orientation to. I can see when my function was enabled, and then it was waiting for resources. And in this case, it didn't need any. We have no triggers, no resource elements or anything like that. So it ran, it finished, and the simulator is also going to show me the time that it finished. Now let's add a few more things to our behavior. And see this in simulation. Note how the timeline is going to indicate the order of execution. First, second, third. I can hit recompute here to see them in their default order. Again, very simple, one thing after the next. Now we're going to build on this and get more complex as we go. Let's start by adding a select construct. And then I'm going to move a few things around here. I'm just using Control-X and Control-V to cut and paste right now. And I'll just use Control-X to cut that one off. Now when a select construct is encountered, only one branch is selected. By default, there's equal chance of a branch being taken. Let's see that here. And again, we see just first function was executed, so it clearly took the top branch. And in the transcript, we can see in the second line where the select was encountered. Now you might wish to weight the selection of a branch, and this can be done by editing the selection probability. If you right-click on a branch, you'll get several options, and right here is the Edit Selection Probability option. I want to show that to you now. We're going to come back to it a little bit later and start making those settings and using them in a more meaningful way. Now we've seen a select. Let's take a look at this in a parallel instead. Just a moment while I rearrange our functions. Now with a parallel, both branches are taken and traversed at the same time. Let's see that happen. And here we go. Now, we can see that they started at the same time, and if we were to zoom in really close, what we would see is that they did not finish at the same time. Actually, if I click on them, we can see that the duration of second function, if you look up in the top right corner, was 10.586. The duration of first function is 10.812. Remember I said that the duration is going to be selected using a normal distribution. This is not the duration of the entire simulation, but rather duration of each function independently. So that's why we see here when we click on them that we can note that each one of them finished at a different time. If the distributions had varied more, we would be able to see that more visually on screen. Let's say that first function outputs some data that is input to second function. Now, this is simply a data store. It has nothing to do with control of the model and simply represents something output from one function and input to another. Let's see that. Not much change, as you can see in the timeline. However, in the transcript, if we come down, we will see some data represented several times here where it is output and input. Now let's change that to a trigger and make this something that has effect on control. I like to do this in a property sheet. There's many ways to do this. There we go. Now I've transferred that over to being a trigger. Now, triggering items do control the model. As shown, second function cannot execute until it receives some data. Let's see that happen here. Now note the timeline with the yellow block. This shows that second function is enabled, but it's waiting for its trigger. It could not start until it got it. So right at the completion of first function, we see the green block start, and that green shows us where the function that was waiting for its trigger was enabled and was performed. Now, so far we've only looked at flows that execute once. Often we need to operate this repetitively, and the iterate construct gives us repeating logic. So let's add one. Now this is asking me for a domain set. A domain set element defines the number of iterations to be used. The default setting is 3, so I need to do nothing at this point to make it use that default. Let's move our behavior inside of that. I am using a interesting keyboard combination. I'm going to hold down Control, drag a little bit, let off of Control. I'm still holding my mouse, and then I will drop it where I want this to go. And if we give a moment for my screen to refresh, we'll see that it moved. Now, let's see this happening in iterate. Quite simple. We see the same thing repeated just 3 times. We've only seen basic models where one function progresses to the next. Most models need more complexity. And multi-exit functions have multiple exit paths that represent a select of next steps given a condition. So let's add some exit conditions to first function. We're going to put in bad application, incomplete, good application. Our sample here is going to start to reference things that look like building software. So we can see we have the 3 options as it leaves first function as to which branch is going to be taken. Let's put some functions on here. And so when we have a bad application, we will fix it. When it's incomplete, we'll do more work. And when the application is good, we'll move on and do whatever is next. And let's see that simulate. Now the simulator is going to generate a random number and to select the branch. If we run it again, the results may be different because a different random number is generated. If you'd like to control this, instead of it happening by random number, you can adjust the selection probability that I mentioned before. There are no constraints on what you can enter here. Core will normalize your entries. If only some branches have selection probabilities defined, any branch without a probability will be treated as having 0. So let's set our probabilities right now. In our sample, our application is a little bit immature, and we're going to assume that we're going to have bad applications more often than not. Now note the sum of these settings, for those that are fast at math, is 109. CORE is going to normalize this to 100%. Let's also change the number of times that the iterate is going to repeat. Now I'm going to use the diagram elements table down here. This is a simple table that shows you all of the elements that are involved in this diagram. It's a great way for me to get to this domain set really fast. If I click here, then there, I can adjust the count attribute that I had selected, and we're going to set this to 10. Let's go ahead and move this back down so I can get my screen space back, and let's see this run. There we go. We see that first function definitely is executed more often, with fix application being next, and do more work happening least often. Now you'll often want to decompose a function into lower levels. So let's do that. Let's open an EFFBD of second function. I'm just going to right-click, open element, and jump straight to the diagram. And let's put some behavior on here. I've already preset some for us. We will receive the application. We'll review the application. Then we'll process it. And we'll go ahead and give it a trigger. There we go. Now let's return to the top EFFBD and note the square in the top left corner here. This indicates decomposition. Now I can tell the simulator whether or not I want to use the decomposition. And there's an attribute for that. Allow me to show you really quick. I believe it's on the secondary tab here. It says execute decomposition. It's by default set to true. In this case, the attributes of second function are ignored, and the attributes of the child function are used. And the opposite then would be true if it were set to false. Let's go ahead and add one more function to our bottom. Forget which folder I put this one in, I'm sorry. There it is, process order. And let's reset and run it. Here we go. Now note the timeline with the diagonal lines. This is something Sara mentioned. It represents the duration of the decomposed function. The child functions are also represented. So we had receive, application, review, and process. They're all up here in these first three lines and also represented here. Now a loop causes the simulator to repeat the enclosed logic. So let's replace our iterate with a loop. Going to use that neat control keyboard combination while dragging again. And wait just a moment for my screen to update. And let's remove the iterate. Now, as shown here, the logic would repeat indefinitely. We just don't have a way out of this loop right now. You would have to stop the simulator to get it to cease. A loop exit provides the mechanism to terminate the loop. So let's add one here on the bad application branch. When the loop exit is encountered, the simulator will jump to the innermost closing the loop node. So it will go from here to here, and then it will proceed. Let's add one more function at the end. Let's also change our selection probability to reflect that our development of our application is maturing. We're going to assume it's good more often than it's not. And let's see this. Now your results here are going to vary. Let's open that up a little bit. But what you'll find is it will always stop after running the bad application branch and then run the stop work function. Now sometimes you need to use a kill branch. When a kill branch is completed, all functions within the parallel construct immediately stop, and control is transferred to the construct following the parallel. Let's modify our behavior just a little bit, just set it up to use a kill construct. We're going to add a branch. We're going to take this out of the loop. Wait just a moment for my screen to refresh. This is a lot for it to move. And let's take away the loop. Now we're going to put a loop on the top branch because what we want here is for this bottom branch to ultimately be our kill. So we don't want to get out, and we no longer have a loop here to exit. So let's put a loop up here on the top branch. And we're going to move everything here within it. We'll go ahead and take out the loop exit as well. Let's do the same to the second branch. Now we're going to set this one to kill. To do that, you right-click and you'll find toggle kill status. Just set that and you'll see that it is now reflected under the branch with the word kill. And we'll go ahead and add a function here so that when all of this is done and we're ready to get out, it's going to prepare a report. And let's give that prepare report a trigger. There we go. Now all the branches in the loop will terminate upon completion of the kill branch behavior. So after prepare report finishes, everything stops right where it is. Any resources that were captured by functions get released. Functions that normally would produce resources don't. Everything stops and goes on to the next function. Let's see that. And we can see here that's really clearly represented. Everything stops at the same time stop work begins. Now, CORE provides modeling capability that integrates both the functional and the physical views of the system. This allows you to evaluate the feasibility of a proposed architecture once the function's allocations and This allows you to evaluate the feasibility of the proposed architecture once the function's allocations and the association of items to links is completed. COREsim evaluates 3 attributes of links and items. Those are delay, size, and capacity. Now we do have an equation that we use for transferring that, and what you do is you take the item size divided by the link capacity and then add that to the link delay. You'll find that formula in our COREsim user guide if you'd like to see that in writing. Let's take a look at a model that I've prepared. I'm going to switch to a different project. Now I have set the size of some data to 0. I've set the link capacity to 1000 and I've set the delay to 0. Now it would be helpful when we're working on these kinds of things to show items and links in the simulation timeline. So we're going to go into user preferences and set that. So I'll click Tools, User Preferences, then COREsim, and add check marks for display items and display links. Now let's open our simulator. And there it is. So we can see our items are represented here. We don't really have any delay going on. Let's increase the item size and see what impact that has. So we'll open up some data, go to the size attribute, change it to 1,000. I realize that is a big change, and I am exaggerating a little bit for the purpose of the demonstration. And now you can see that we have a delay happening here on the link. There's a minor increase in the simulation time due to the delay caused by the time for the link to transfer the item of this size. Let's adjust the link delay. I'm going to get to the link through the item that is transferred. See, here we have transferred by link. So I'll open that up. And we're going to set the delay to 0.5, so a minor change. And we see that the delay has increased. Now this can be used to determine the effects of interfaces and constraints on those interfaces on your system design. Now resources are different than items. They generally are something that is produced, they're consumed, they're captured, and they allow you to investigate system resource requirements and the effects of resource contention on the timeline. Now there's a difference between a resource that is captured versus a resource that is consumed. A captured resource is released when the function executes and is available for reuse. The RAM on your computer is a good example. A consumed resource is never let go and cannot be used. Printer paper is a good example of that. Let's switch over to a different behavior model that I've prepared to demonstrate resources. And here we see first function produces MIPS, and the notation here is a little bit different. When we had an item that was passed, you didn't have this half circle coming off of the blocks. The half circle helps us see that it's a resource. Also, the concentric circles around the resource is another visual indicator that we're looking at a resource and not an item here. Now I've set the initial amount to 2. This tells the simulator when you're starting the behavior, how many of these things do I already have in my pile waiting for me? So I've set that to 2. I've also set some relationship attributes. First function produces MIPS, and there's an attribute on that produces, and I've currently have that set to 2. The consumes relationship also has an attribute, and I currently have that set to 4. Let's see this in simulation. And it failed. Take a look at my blocking events. This is precisely what I wanted to see happen, and I'll admit to having rigged it to work this way for our demonstration. And we'll start looking at it from the bottom. In something that's more complex, with lots of triggers and resources, these blocking events are going to be even more important. With this small behavior that we're looking at, any of us could just quickly look and know where we failed. But in something bigger, we're going to need this blocking events dialog. So you can print it and save it so that you can reference it later. But I'm going to start looking at the bottom, and it tells me receive application would not start because it didn't have its resources. So I'm going to use this information to change our model a little bit and help it along so that it'll finish. We're going to change the initial amount. Let's go ahead and open up MIPS and take a look here. I mentioned the initial amount attribute was set to 2. I'm going to change that to 10. Now I also mentioned some relationship attributes. It is produced by first function, and here's our relationship attribute that's set to 2. It's also consumed by, and we have that amount set to 4. Now you may have noticed I have another consumed by here, and I have it set to 3. And here's what's interesting. Remember that I talked about the execute decomposition attribute and how that causes core to go to the children. So I have this same resource being consumed by second function and consumed by receive application. I've set it down here as well. And because I have the execute decomposition set to true, it's ignoring the setting for second function altogether. So even though I've set them at different numbers, it's taking the one of the child. It's an important thing to catch, and something that honestly caught me up for a minute until I sat down to investigate why I wasn't behaving the way I'd thought. So let's reset and run this. There we go. Now this time, it's at least failing in a different place. But if I keep running, I will likely get to some point where it finishes. There we go, because it got to this loop exit before it failed. So I'm clearly not yet done refining my resources to get them to the point where we're going to have enough produced in order for this to run through the loop reliably before it hits the exit. So I have work to do still. We'll abbreviate that, though, for the purposes of this demonstration. Now, before I go, I want to make a note on enhancing simulation further. Our scripting environment, or language, I'm sorry, is called COREscript. And this is a procedural-like languages that allows you to do a whole lot of things in core. We run utilities with it, we output reports with it, and in simulation, you can also enhance your model through that. Now, it allows a user to vary input conditions and logic from one simulation to the next, as well as collecting data in alternative formats other than the timeline to do more detailed analysis. Now, COREscript is beyond the scope of what we can teach in this webinar. So I want to point you to one resource. First is Section 6 of the COREsim User Guide, which is going to give you an introduction. There's some folks out there listening today that can take a look at that and get going. Now, we also offer a class. It's called the Fundamentals of Core Scripting. It's a 2-day class that gives further study and teaches COREscript in depth. So you can send an email to our team. It's info@vitechcorp.com if you'd like to know more about that Fundamentals of Core Scripting class. Katie, that finishes our prepared information for today. Do we have questions?
We do have some questions. The first one I have is from John, and he's asking, how does one run multiple iterations of the simulation? And for that matter, how does one simulate an alternative model structure? That is, like structure A compared to structure B.
Okay.
Sarah, would you like to take that one?
Yeah, I can. So to run multiple iterations of the simulation, you can, if you are wanting to essentially have the thread iterate through, Bethany showed you how you could put an iterate on that. However, if you aren't looking for that, what you could also do is just manually run them and then run the simulation once, the simulation again, and the simulation again, and compare the results for each one. And then if you needed to, you could change essentially the probability of your branches on your simulation to see how the behavior would change with each simulation that you're going to run. The second part of your question, you could do this in a couple different ways, and it really depends on what you're wanting the outcome to be. So one thing you could consider is you can have essentially model 1, which would be like alternative A, model 2, which would be alternative B. You could just run both models in your simulation and then just manually compare those results. And that's pretty, that's a pretty simplistic approach. If you're wanting essentially a way that you can have the two alternatives in different spaces, what you may want to consider doing is creating cross-project relationships between those alternatives in different projects. That way, what you could do is you could still run the simulation on one versus the other, but they would be in completely different models, and that would allow you to essentially try to figure out what those alternatives could be without it being integrated into one project. You could also consider making the two alternatives as branches under one parent. And this would allow essentially the simulation to be kind of, I'm going to say, and this is a bad way to say it, but kind of integrated in within the same model. And then you could look at it in that way. And you could also consider maybe doing a composition BDD, block definition diagram. And this would allow you to show two different configurations of the system with that composition BDD. And because you can run simulation on a structure or on like a element, so a component, that would allow you to run the simulation on alternative A, and then run the simulation on alternative B, and then compare what those results are. So there are actually many ways to do this, and it really depends on what your project is, what your model looks like, and what you want your outcome to be. But I hope that gives you some different ways to consider. Okay, what's the next question?
All right, thank you. Yeah, I do have another question. I've got one from Carrie. She asks, is there a way I can specify a maximum time permitted between functional enabling and the start of execution?
Yeah, so earlier, Bethany opened up a function. If you want to do that, Bethany, that would be fantastic. So on the property sheet, if you go to the secondary tab, you will see the ability to set a timeout. So what that means is depending upon what that timeout time is, the function would wait that amount of time, and then if it couldn't execute, it would essentially time out, and then the execution of the model would just continue as planned. Okay. Next question.
Okay, thank you very much. I've got just one more. It's from Sean, and he asks, what diagrams support the COREsim execution?
Okay, so that's a very good question. So you can actually run COREsim on any of the behavior diagrams. However, COREsim uses the logic and the EFFBD and the activity diagrams to run. So you can run them on any behavior diagram, because keep in mind that all of the behavior diagrams are looking at the same underlying data model, so you can launch it from any of them. However, what you are seeing being represented in COREsim will be what you created in an EFFBD or in an activity diagram. Okay, is that it? Or do we have any more?
All right, thank you so much. That is all. Those are all the questions that we have for today, but I imagine that some of our viewers today, once they get a chance to get in and start working with it, we'll have some more questions. So if you do have any more questions, please don't hesitate to shoot either of them an email. And I believe we've got their email addresses on the screen now, and they'll do their best to help you out. Or you can post your questions and comments on the Vitech LinkedIn group page. Just visit linkedin.com and search for Vitech Corporation. You'll see our logo there pop up. You'll be able to get onto our group page. And that does wrap up today's presentation. I'd like to thank all of you for joining us. And please keep an eye on our webinar calendar for the next webinars that are going to be coming up. We do have one coming next week that is going to feature Embry-Riddle and the work that they are doing with CORE for the NASA CubeSat project, and that should be very interesting. You can also now register you can actually subscribe on our site to get updates about webinars, so you can do that on the Vitech homepage. And in addition, at the conclusion of this webinar, a survey is going to open on your screen. Please take a moment to give us some feedback on today's presentation, or to let us know what topics you'd like to see covered in future webinars. Thank you, everyone, and have a wonderful day.